Okay, thank you very much. Okay, so I'm luckily I didn't come in person because I just got over some COVID, but now everything is fine. So this work is in collaboration with a postdoc that I'm working with at the Universidad Católica de Chile, where I am. Now I'm actually not there, but that's my affiliation. And then so basically, as the people who know me, they know that I have worked with energy minimizing configurations and so on. So I just to let you know a little bit how was my motivation to come to this. So it started from this observation that all configurations in spaces like RD, homogeneous space like RD especially, are always very regular, yeah? And then one tries to prove this regularity, which usually means periodicity, or if you cannot prove that you get a lattice minimizer, then you try to prove that it has some repetitivity properties, some property like hyperuniformity, or absence of concentration of points, or absence of holes without points. For example, in the form of quantitative estimates on distances of this point, of the minimizer's points or equidistribution, and so on. So you can try to prove something in a hierarchy, partially ordered hierarchy of geometric properties. But then there are also other kind of points of view on this question about regularity, which is what do you look about what for you are looking for regularity, right? So one property, which is the first one, maybe the nicest one, is that if I have a disordered points, it takes me a lot of time to tell you where the points are. But if you have a lattice, then I take the basis of a lattice and then where every other point in the configuration is, right? So they are in a way easier to encode the regular configurations. But the one I want to focus in this talk is that actually they are easy to recognize, yeah? And so it means that when I perturb them, then I can recover them. Okay, so this is how one possible path to go from regularity of point configuration to these recovery problems, which highlight one property of these very configurations, such as lattice or peak configurations. And so the question I talk about is this one. I consider so that's the setting. The lone set is a set which is R separated. It means that no pair of points in my set are a distance smaller than R. Yeah, so you have to think a subset X in RD, subset of RD. Yeah, and then so there is a separation between, and then there is no radius R without any point in it inside RD. And then so this is the lone set, and we are always working with the lone sets. See, so here I consider the set of all the lone sets for some choice of parameters, and then we are going to choose some kind of regularity class of our sets in here. Yeah, this is in general, this kind of problem works like that. And then for X in my nicer the lone set class, I'm going to look at the perturbations of it. These perturbations in general will not be the lone set. And they have the form that every point is having a little change. Yeah, so psi p will be a perturbation of the point p. So I perturb all the points in the set, and I get this set x psi. And then the question I'm going to ask is there a principle that allows to recover x from the knowledge of its perturbation? Well, under the hypothesis that my set X is in my nice class, yeah, because if my class is so large that X psi is also in the class, then of course you will not be able to recover X you have to make some restriction on the class of X that you talk about. Yeah. So we have this kind of a problem in general that we are talking about. And okay, and so the kind of results that so you can have many different kinds of the type that you can recover the set. Oops. Did I lose my sharing? I clicked for something. Yeah, I hope everything is okay.
No,
okay, so we are looking for, so we have this kind of result from Yakir from 2020. This is the case of random perturbations, right? So we have a random vector valued random variable with its probability space. And so we consider perturbations. I have a change for every point in my set X. And I consider the case that these are independent copies of the same random variable. Okay, I perturb I flip a coin and I get a vector for every point, and I get a perturbation of my set X with this choice of perturbations for every point, independently for every P again. And then the result of Yakir is the following. It says that if X is a lattice, and if this perturbation has some moment decay property, then almost surely for every vector lambda, when I take this kind of, if you look at the sum here on the left-hand side, you can see it is like a Fourier transform of the set xi. I take for every point in this in a ball intersected with xi, e to the minus 2 pi I, the interior product between x and the vector lambda, and then I take I'm averaging and taking r to infinity. So this is in an average version of the Fourier transform of my perturb set. And then the result of Yakir said that's almost surely for every lambda, this is equal to either 0 or a fixed number, a number depending on psi and on lambda. And actually it is the so-called characteristic function of the random variable psi calculated in lambda. And so this is what happens if lambda is a point in the dual lattice in X star, which is the dual lattice of X, and otherwise I get 0 if I'm not in the dual lattice. And then, so this is a formula about the Fourier transform of my random set, but then it is also implying a recovery result, which is for example, in the case if phi c is always non-zero, for example, if c is a Gaussian distributed, this is happening because then you have the exponential is never 0. Then you can divide by phi c, and then you can find the Fourier transform of the masses in my lattice, and then you can recover my lattice. Yeah, I can recover x star, and then I can recover x. And then this means that if I am looking in the class of lattices, these are recoverable from perturbations of this kind. This is the recovery problem that with Rodolfo we found, and we find it very interesting. And the proof of it was very enlightening. And so we tried to extend this proof and to get some extensions of this result, right? So. So basically, the kind of extension that we get are for sets of this type that satisfy some hypothesis. And what we are looking at is sets X. Always imagine that these sets are in RD. I always just skip this hypothesis because it seems we are so used to work with sets in RD that I don't even mention it, but actually X is in RD. And then it will be a Delon set, yeah, also. And then we are looking at sets that have an asymptotic density, so that this limit exists limit for r going to infinity of number of points of x in a ball divided by the volume of that ball, density. And then we have we have a hypothesis about the diffraction measure of x. Yeah. So that diffraction measure happens is something that comes up related to applications when you have a crystal and you send X-rays in it, an X-ray to my set. Then I'm looking how does the diffraction of this set work by checking the intensity of the energy from my X-ray depending on the direction in which I send my X-ray. Okay, so I have my the diffraction measure is defined as this. You have here something like the Fourier transform to the square, right? So let me erase this. Okay, so you have the sum for the points in a ball of e to the minus 2 pi I p interior product with y to the square, and this would be a function, but I consider it as a measure, right? Should I put here dy just to recall that this is a measure? And then I take this limit in the sense of measures, and this is the diffraction measure of the set x. Yeah. It is also related to the autocorrelation measure, right? So usually this gamma x would be the autocorrelation measure of my set x, which is basically a measure that tells me how the distances, how the x minus x are distributed for what are the positions of x minus y with x minus y in my x and y in my set x. And that would give me the autocorrelation measure. And the Fourier transform of the autocorrelation measure is this diffraction measure, which is really what you see in an X-ray of a crystal. Yeah, something about the diffraction measure. And usually, depending on the direction in which I'm sending the X-ray, which is given by this y. And then, so basically, all of this is part of what is called the mathematical diffraction theory. Mathematical diffraction theory, and I can mention the book A Periodic Order. It has 2 volumes, which we were studying together. This is by Bake and Grimm. Yeah, and so I'm not getting into the details because you have a lot of details. I mean, that's in quotation mark details, because you have to have hypotheses in your theory of diffraction that tells you that there are these measures which are not finite but are locally finite, and you have to put the lowest possible condition on regularity of these measures that allows you to still have a theory and still can take Fourier transforms and so on. But anyway, I'm a bit skipping this part because I feel like there is a so that once you understand kind of the concepts, then you can fill in the details as a second step. And I'm trying to give you the main message here without the technicalities. Okay, but so the point is that we have these 2 hypotheses. The first is that there exists a density for our sets, and the second is that we have a diffraction measure, and that is a locally finite random measure, which important thing is that we assume that it's singular with respect to Lebesgue measure. Yeah? So my set X is not so bad that it will give you continuous diffraction. Yeah, is close enough to a crystal that you can still see a singular diffraction measure. Okay, so examples of these 2 properties. The main examples so the most regular kind of examples are the so-called cut and project sets. Yeah, so it was proven by Hoff that the cut and project quasi-crystals that include Penrose tilings and whatever it is you can mean by most quasi-crystals, the ones that are appearing more in the literature. So these kind of examples are given by here I take the space RD mass K, a space of higher dimension. Here it's D plus K is equal to 2. And then inside this space, I take the neighborhood of a subspace, usually with irrational coordinates. So I have a subspace which is identified with RD. I take a neighborhood of this subspace, which is given by a sliding window that is going to give me this orange band. Whatever is in the intersection of a lattice. I have here a lattice in my space RD plus K. I intersect it with this band, and then I project to RD. And I get a subset, which is not really periodic, but it's periodic in the sense of these definitions of quasi-periodicity that include this kind of sets. And then this set satisfies these two properties. Yeah, that the diffraction measure is singular with respect to the Lebesgue measure, and that it has an asymptotic distance. Another kind of sets here, there is also a theory of Meyer sets that enter into this hypothesis, and these are sets that are such that x minus x, the Minkowski difference of x in itself, it's discrete, is uniformly discrete. Yep, these are Meyer sets. Okay, so there are several classes of Meyer sets that also satisfy this H1 and H2 condition. Okay, so these are the new sets that are included in here besides lattices. And then the theorem that we have is a first theorem. We have three versions of this kind of theorems. So the first theorem A that we have is that if you have a Delon set that satisfies this hypothesis, like in particular, you can think the Penrose quasi-crystal, for example, could be such X. And then you have the Xi-P, which are, as before, identically distributed, independent, and have this control on the moments for epsilon bigger than 0. And then again, you can have the same result. You have that what is here, this average type Fourier transform of my perturb set, Xi. I can relate it, yeah, Xi, I can relate it to the same object for the unperturbed set, X. And here I have again, as before, the characteristic function of Xi calculated in lambda. And this holds almost surely for all lambda, yeah, contemporarily for all lambda. So again, you can divide by this thing, this red function here, and obtain, recover your Fourier transform of X from the Fourier transform of Xi. Okay, so here is written in a more compact notation. If I have a set X and I write a Dirac X to abbreviate the sum of Dirac masses at all positions in X, then the same formula from above becomes that the Fourier of Dirac at lambda is equal to the characteristic function times the Fourier of Dirac of the unperturbed set at lambda. So you have this kind of factorization of the Fourier transform, right? And so maybe this is the time to kind of sit down and interpret a bit this formula. Basically, this formula is kind of has the meaning that, like vaguely speaking, roughly speaking, the set Xi is like if I look at the Fourier transform, it is as if I would take a convolution of the Fourier transform of the convolution of a function related to the density of Xi with the law of Xi convoluted with the sum of Dirac masses in X, right? Because you remember, so the Fourier transform has this property that transform of a convolution is the product of the transforms, right? So the theorem is telling you that almost surely, when you measure for an instance of I measure my Fourier transform, I see the same as if I would take the law of Xi and the convolution of this with the deterministic set X. So in that way, I can recover it, right? And again, let's do another step of speculation. What it tells you is that in a way, by doing this, that I can think of this IID repetition of psi-p, simply repeat experiments. I repeat experiments, and I can have a law of large numbers that tells me that they are going to, the fluctuations are going to cancel out their discrepancies, the fact that they are random, if I take this Fourier transform over the whole of space. And so this is a bit the principle, I would say here. This you have such much regularity in X that when you average over the whole space, you take Fourier transform, this different kind of random behavior of the Fourier transform is canceling around, and in the end you see the same thing as if you would take infinitely many experiments of this repeated experiment of this psi. Okay, and again I formulated the same as before, that if phi psi is 0, then I have that the sets, now this kind of quasi-crystal, quasi-periodic type sets are recoverable as well. It's a little bit extension in this type of regularity of our sets that is allowed. Okay, here I have to, because it's very common in the literature, if you know works by Torquato and people from material science, you have that question of recovering the diffraction measure, or maybe even more, you have recovering of the structure factor. Yeah, so the structure factor of a configuration is pretty closely related to the diffraction measure, and to recover this this property of the set from its random perturbation is a different question than to recover what we are doing here, to recover Fourier transform, right? So it's a little, it contains the diffraction measure, contains a little bit less than the Fourier transform, but also contains the square. So it is a more nonlinear problem to study the recovery of the structure factor, because it contains a square. It's like a square of the Fourier transform in an averaged way. Okay, so just to make mention this difference. And it's an open question to extend all this theory towards this theory of recovering the structure factor instead of the Fourier transform. Okay. Did I jump something? No, sorry. Okay, so now I am going to tell you a little bit about the proof. So the proof, I have this proposition. It's telling me that almost surely for all lambda, I have that this limit goes to 0. It is the limit of sum of, so the average over larger and larger balls of Fourier like the Fourier coefficient corresponding to a point in X, plus the difference between the Fourier transform of psi-p, of the Fourier transform of my vector psi-p, and here the average. Yeah, this would be the expectation of the same thing as, so this is like the expectation of that other part. Yeah. And so we are saying that these two quantities there are some larger balls in average that tend to 0. This is the first step. And the other step is this, which is telling me, so you have here again an average kind of quantity, and here I'm looking at points if let me make a drawing. I have here radius r. I'm looking for points such that either P is inside the ball of radius r and its perturbation is going outside, or vice versa. Yeah, so I'm saying that the signs of length of P minus r and length of P plus its perturbation minus r, these have different signs. Yeah, so I'm saying I'm looking at the number of points that are jumping across the radius, across the boundary of balls of radius r. And basically, this is what my moment condition holds for. If I have this moment condition, then I can find that almost surely asymptotically this number of points is less than a volume term. Okay, so if I have these two steps, then I have the theorem. If I have proposition plus lemma, then I have the theorem. And so here I wrote down the statement of the theorem. So you have here in the statement of the theorem is the sum over psi p point, a perturbed point in xi of the Fourier kind of term coming from it. And this should be equal to this in the limit. And if I would imagine that I bring these terms to the left, then I get really some term of this kind. Yeah, I get really the same statement as in the proposition, except that here I have that points are. Wait, let me. Yeah. So it just except that here I have p plus psi p should be inside the ball. Yeah, and then here instead I have that p should be inside the ball, right? But the discrepancy between these two sums here is controlled by the lemma. Yeah. So the role of the lemma is to replace in the sum, instead of having sum over x, I have sum over x psi, and then the proposition is going to tell me that the statement of the theorem holds, right? So the main difficulty now, the lemma is not so hard, but the main difficulty is the proposition, to prove this proposition. So proof of the proposition, what is telling me the proposition is the product of this times this, summed average is going to 0. So it's telling me I cook up these two measures here. Yeah, I put a Dirac mass in front of these terms and Dirac mass there. And I am saying that it's going to say in a way that seen as a vector in a Hilbert space kind of framework, that mu x is going to be orthogonal to mu psi. Yeah, this for all lambda and almost surely. And then, yeah, so here I mention again this reference that is what's going to help in this framework. And also I have to mention that like the proof strategy and the proof kind of dynamics here is was done for lattices in the work by Yakir, and the goal for us was to extend this as much as possible, right? And to enter it into the setup of mathematical diffraction theory. Yeah, to go as far as possible with these ideas using only the Fourier transform methods, right? So basically, the main theorem that we are that is useful here is this one below, where I have this. So if I have two measures mu and nu that are going to be related to these measures here, in the end, then I have two measures. I can consider any measure sigma that is such that the two are contemporarily absolutely continuous with respect to sigma. Yeah, for example, I can take the average. Sigma could be the average of mu and nu. So for any such sigma, I can take the how is it called, the Radon-Nikodym derivative of the two measures with respect to sigma to the 1/2, do the product, and I define this, which is called is a density referred to Hellinger, like a Hellinger Hellinger kind of distance between mu and nu. And I have this theorem which has two parts. So one part is that when I have a sum like this, I have a function which is here I take any compactly supported function, yeah, and then I take these averages that are is like the Fourier transform of f tested against mu tensor nu conjugate and integrated over and summed over this ball. Then this lim sup is controlled by the Hellinger distance tested against f, Hellinger distance of the diffraction measures of mu and nu. And then this Hellinger distance, it's easy to see that it's 0 if the two diffraction measures are mutually singular measures. And in fact, here this is interesting for us. I put this hypothesis because it's interesting for us, except especially for f positive function, because in that case, if this is zero, if this here is zero for all positive function, is the same as saying that that this sum here on the right, this kind of convolution of measures is zero, and then so from this theorem position, we have to take which is concentrated to at a distance smaller than the point separation by the lone sets, and then this actually in that conditions this sum in parentheses is really the same as just the p equals q case, which is the one from the proposition. So I'm looking for this for a concentrated f depending on the lone property of my set f. And in order to obtain the proposition with all this setup, I have to prove that the diffraction measures are orthogonal. Yeah, this is the same as was needed in the case of lattices in Yakir. And then to prove that the diffraction measure of my two measures are orthogonal, first of all, one of them, the one for the deterministic set, I'm going again back 2 slides. This is actually just wait a little bit 1 slide. Yeah. So this one is just the translation of the Fourier translate of my mu. Okay. So where is it? Here. So the diffraction measure of mu x lambda is the translation of the diffraction measure of x, and since I have by hypothesis 2 that this was then I get that I know that this part is singular with respect to Lebesgue, and so the hard part is to prove that almost surely for all lambda gamma mu psi lambda, so that the diffraction measure of this other part is absolutely continuous, and then in that case I would have that that the two are singular, and I conclude my result. And so actually the true thing is that we get is that is actually not only absolutely continuous, but I know exactly how it is. It is actually just like an oscillation, yeah, like a wave. It will be just a wave. It is the Fourier transform of a Dirac mass at 0. So actually it's constant, sorry, not a wave, because the Dirac mass at 0. And so I have this kind of characterization, which if I prove this lemma, then I conclude the proof. And so I don't know till when I have time, but maybe I can jump the proof of the lemma, because I want to conclude. Right, I think I have till basically my time is almost over, right? 25, yeah. So yeah, let me 25. Jump maybe the proof of the lemma. And so I just mentioned that we have another theorem which is extending the other part of the result, right? So here is we are having this other version where you have the lone set that satisfy H1 and H2. The same hypothesis on the noise, on the perturbations, and then we assume that the perturbed configuration gives a stationary process. Yeah, and this stationary process, it means under the action of RD. So it means that my noise is such that when I perturb my set, I am in a stationary process. Yeah, as Xi stationary and weakly mixing. Yeah, it means that there is a lot of decorrelation in my set, weakly mixing. And then again, I get the same kind of result. That here, if I take the Fourier transform of the perturbed set, this is decomposing. He has written in an opposite order, but it's just my fault. I should have written it in the same order as in the other results. I have this term that is it's not really. I have to write it in this order because here I am not assuming. I'm not assuming that they are neither independent, no, and then I don't assume that they are identically distributed. Yeah. So in general, I have a different characteristic function for every p, but still I can obtain that. And here this is depending on p, right? Here it's not. If the xip would be identically distributed, I could put this term in front as a factor, and I would get the same as in the previous result. Okay. So you can. So basically, this is the other type of result, right? That you have, if you have weakly mixing, after you perturb, you obtain a weakly mixing stationary process, you still can recover. And this is based on the work by Guéret, where you are studying stationary processes, and he studies the Fourier transform of the Palm measure, which is kind of an autocorrelation measure for these stationary processes. And then to obtain the absolute continuity, here it should be with xi, not with x. I'm sorry for the typo. There is a criterion from people from dynamical systems, which is quite straightforward, that we apply. So we extend a little bit this work and we get this other result. But here, and then we have examples of some kind of random cut and project quasi-crystals for which we can not have perturbations that are really distributed or that are independent, but still, if the result is a weakly mixing stationary process of the perturbation, we can recover it, and we have an explicit example of that in the paper. And then here I want to emphasize this. This is something that we didn't, is something for the future. We didn't completely solve it. Kind of this theorem C is a bypassing of this problem, which is that in order for my interpretation of how the noise is, how I get rid of the noise here, in order for this interpretation of how I get rid of the noise to work, that is that here actually is every time I perturb it, I'm doing a kind of independent experiment and so on. And actually what is really useful here is not that these xip are independent, but really that it's only compactly many of them that count. Yeah. So if my process is stationary, then I can compactify. I can use my action by translations to really say that actually just what happens in a compact set is useful, and I use this. This is kind of a kind of weakening of the independence, which is needing that you can compactify your space of perturbations in a way. And if the set is periodic, is easy, but if X has no precise periodicity, if X is a quasi-periodic set, there is an interesting interplay between what it means stationarity and how can I quantify this almost stationarity that I get in order to get this kind of splitting of the Fourier transform as if it was a convolution. Yeah. So there is a conceptual difficulty there, which is bypassed by our theorem C. But it's an interesting question. How can you define stationarity or quantitative almost stationarity for a periodic set? Anyway, so that's all. Here I have a summary, which is saying that I have periodic and quasi-periodic configurations. They can be perturbed under IID perturbations. Otherwise, I have to, if I don't want IID, I have to put weak mixing conditions. And there is the problem with the structure factor and how to define weak mixing under quasi-periodicity. And that's all. And so I hope everybody will almost surely recover from the pandemic and that we meet in person soon. Anyway, so thank you.